Okay. Okay, so welcome. So this will be our first week's tutorial of this course, Introduction to StatMech. So basically my plan is to first cover the assignment that is already given in the course portal, that is the old assignment, which you can see probably now in my screen. And after we cover that, because it will be a 2-hour tutorial session as you know, so after we cover that, I plan to give some extra problems, some extra assignment sums that we'll also solve together. Okay, so basically I think these assignments are not graded or anything, but you have to submit it. There is a due date mentioned, that is 7th February in this case. So we'll first try and solve these problems, and then later on we'll move on to the extra problem sets. Okay, so in any point, if you are having some problems with my audio or my screen, or let's say if you are having some problem with the explanation of the sum I am giving, so just feel free to interrupt me and I'll try to solve that. Okay, so let's start then. So this assignment has 8 problems. Okay, so let us start with the first one. It is an easy one. We'll do this together. So in some point I'll ask you if you can if you know the answer, then you can tell me, and otherwise I'll explain the explanation, whatever that is suitable. Okay, so the first question is entropy of an isolated system always dash and becomes a dash at the state of equilibrium. Okay, so can any one of you tell me the answer? What will be the answer to this blank space? The entropy of isolated system always, what it should do, increase or decrease? Hello, any one of you, if you know the answer?
I think it should increase.
Yeah, right. So yeah, that is correct. Entropy of the system should always increase, because you know from second law of thermodynamics itself that entropy of an isolated system can never decrease. It is always either constant or it should increase, right? But in these options you are given, there are two options, either decreases or increases. So just someone has joined, let me, yeah. So the obvious answer will be it increases, and then it becomes a dash at the state of equilibrium. So what will be the answer? It will be a yeah, so let me tell you once. It will be a maximum at the state of equilibrium. Okay, so let me just take the pen. Yeah, so the answer is entropy should increase, this answer, and it will be a maximum at the state of equilibrium. Now I have told you the answer, but just for the sake of clarity, let me the Wi-Fi is having some problem. 1 second. Okay, I think the connection was lost in between, but right now I think it is fine now. Okay, so we are discussing the first problem, that I was telling you that I should also explain why the answer is that option that I chose. So basically we are given, let me take this pen instead. So we are given an isolated system. Okay, so an isolated system, that means it cannot interact with its surroundings. So it cannot interact with the surroundings. So its entropy, that is if the entropy is 1 second, if the entropy is S, then the change in entropy is delta S. Okay. And we know from the second law of thermodynamics that delta S should always greater than equal to 0. So this is basic. I think even in thermodynamics knowledge we know that. This is second law of thermodynamics. Okay, so that is the answer, that entropy should always increase, and in the option there is no constant option, because entropy can be also constant. That means its change should be 0 only if it is a special ideal case, like if you have a reversible process, or let's say the system is in steady state, then only the entropy change will be 0. Otherwise, oh, my screen is not visible. Oh, I think, let me share it once again. Okay. Yeah, now it is visible now. The screen.
Yes, madam. Now it is visible.
Okay, I think in between the internet went off, so after that it had created a problem. Okay, so I was telling you that for an isolated system means the system cannot interact with any of its surrounding. It is completely isolated from anything else. And for such a system, you know that second law of thermodynamics tells you that the change in entropy, that is delta S, should either be equal to 0 or greater than 0. Now greater than 0 is the most likely case, because in our nature most of the processes are irreversible processes. So in case of irreversible process, you know that entropy should always increase. Okay, that's what we choose, the option entropy increases. But there is also a possibility that entropy can remain constant. That means delta S equal to 0 can also be true, but that is only for ideal cases. Okay, ideal cases. What are the ideal cases? Like if the system is in steady state, or if it is a reversible process. Okay, it is a reversible process. Otherwise, delta should be greater than 0. Now, this is the first part of the answer that we correctly chose. But then the second part was that what will be the entropy at the equilibrium point. So, the entropy will be maximum at the equilibrium. Now why so? Because you can be confused, because equilibrium generally means that the systems, whatever properties we can see of the system from outside, what are the macroscopic properties of the system, it cannot change with time. That defines the equilibrium of a system, right? And you know, entropy is a measure of disorder or randomness. Like how many ways are there to arrange a specific configuration is actually tells us the measure of entropy. So in first attempt, many people may confuse that if we are saying that it is an equilibrium state, then why the entropy, that is a measure of randomness, can be maximum instead of becoming a minimum. So this can be a general confusion. So that's why I am explaining this to you, that no, it will not be the case, but the entropy will be a maximum at the equilibrium point, because you know that the Boltzmann formula of entropy is equal to Kb ln omega, right? So where Kb is the Boltzmann constant, and omega is our number of microstate. Okay, so omega is our number of microstate, and so the larger will be the value of omega, you can see that the entropy will also increase. So number of microstate actually tells us how many ways are there possibly to rearrange a particular macrostate. That means if you have a system and it has a proper macroscopic properties, means say it has a particular volume, it can have a particular pressure, if it is a fluid system, then all these properties remaining same, how many ways its macroscopic variables can be arranged. Okay, so that tells us the number of microstate possible for the system. So how many ways are there to rearrange a macrostate microscopically. Okay, so if there are many larger number of S, then S will be increasing, and at equilibrium there will be the maximum number of omega possible. So this omega will be maximum at equilibrium, because at equilibrium state the system can actually cover all the possible way of rearrangements of the microstates, and that's why the entropy will also be maximum for that case. Okay, and you can also in other way think of it like, let's say um, because let's say this is our entropy axis and this is our some energy axis, let's say equal to energy. This type of problem I think you have seen in the lectures, in the week 1 lectures, that for a particular case of system, let's say for a problem of cards, there you saw that for a particular value of energy, initially the entropy was 0, then it increased for certain energy values, reached a maximum, and then again falls down and then again becomes 0. So this was a particular example case from the week 1 lectures, where you could see that for n number of cuts, or let's say here I have written it in terms of energy, but you can also write it in terms of number of cuts also. But you saw that there is a particular point where entropy reached a maximum value, and at other points it was lowering its value and almost close to 0 or equal to 0. So this is just an example problem to tell you that if this is our equilibrium point and here entropy is maximum, then to go anywhere from the equilibrium except the equilibrium, you have to go to a lower entropy, right? Because at all the other points the entropy should be lower than the equilibrium point. But what is the idea of equilibrium? That once you are in the equilibrium system, you are always steady or stable in that equilibrium, right? So that's what you also know from the idea of energy, that once you are in an energy minima, that is the equilibrium, so you can disturb the system, but you are always remaining at the same position, because that is its energy minimum, that is its most stable position. And by the law of thermodynamics, you saw that the entropy should never decrease, that is delta S cannot be cannot be less than 0. So to go in any state other than the equilibrium state, you have to lower your entropy. That in other terms can mean that you have to as if decrease your entropy, which is not physically possible because that is against the law of thermodynamics. So as if you are in an equilibrium state, you are always stuck in the equilibrium state and you cannot disturb the system to go to anywhere else. So this is a very rough sketchy, like not sketchy, it is a rough idea to actually understand why we are calling that apparently the equilibrium, it's a state where the entropy should be maximum. This is just a physical understanding I tried to present to you, that if you are in equilibrium, your entropy should be maximum, because you will like to be in equilibrium forever. To go to any other state from equilibrium, you have to as if decrease your entropy or lower your entropy, which is against the second law of thermodynamics. So basically equilibrium is the state where the entropy is the maximum. Why? Because here it can cover the maximum number of rearrangements possible for the microstates. So the number of microstates omega is maximum, and as a result S equal to kb ln omega, which is our Boltzmann formula of entropy, should also be maximum. So this was the answer. I think it is clear to you now that why the entropy should be maximum in the state of equilibrium. So this is the answer number B in this case. Now the second question is, which of the following statements is true? So there are 4 statements given and we have to choose which one is true. So the first statement, let us read that. So it says that a given macrostate typically corresponds to a huge number of microstates. Okay, just 1 second. Here it is being recorded. Okay. Let me go to full screen again. Yeah. So a given macrostate typically corresponds to a huge number of microstates. That is option number 1. So without going to the further options, I can tell you that this is our correct answer. And why, I will tell you as we go on to the further options. So basically I was telling you earlier about the concept of macrostate and microstate, which I am sure that you have learned from the lecture also. That macrostate is basically generally means the bulk nature of the system, like macroscopically how you describe or explain a system, right? So let's say if you have a fluid system, then the macroscopic properties of the system are mainly pressure and volume, P and V, right? So let me write this also. So we are solving question number 2. I have to decrease the point. Okay. Yeah. So for a fluid system, the macroscopic properties are pressure and volume. So this is the macrostate that is representing this fluid system. And similarly for a, let's say you have a wire, that is also another system. In that case its macrostate will be represented by, let's say, the length of the wire L, and we can say the tension of the wire, we can call it maybe tension tau. Okay, so this is the macrostate for this specific system of wire. And in this way, if I am giving you the idea that by defining some or allotting some macroscopic properties to the state of the system, you can choose to identify the macrostate for the system. Okay, and for each macrostate there can be many possible number of microstates. So this was our actually the option number 1 that we marked to be true, because for any macrostate the microscopic signatures can be different. Okay, so keeping the macroscopic variables to be constant, let's say for a fluid system you can keep it macroscopically identical. That means you cannot change the pressure and volume of the system, so macroscopically the system will look the same. But microscopically, I mean in terms of, let's say, atomic level, when you are trying to rearrange the system, then there can be many possible ways how you can rearrange it microscopically. So as if you are changing the rearrangement from a microscopic point of view, or you are actually exploring all the microscopic degrees of freedom, but it is not changing the macroscopic structure of the system. As if you are changing something microscopically, but the macrostate is remaining the same. So how can we define that? That means you have a same macrostate. Why you are telling it a same macrostate? Because the macroscopic properties like pressure, volume, or for a wire it is length or tension, these are not changing anyhow. So these are remaining the same. That means it is the same macrostate. But under that you have many possible ways to rearrange the system in a even smaller scale, like microscopic scale. There can be many possible number of rearrangements. Let's say in terms of atom, you rearrange the atoms in another structure, but you keep the pressure and volume, these quantities same. So what happens is that microscopically there are many different configurations possible, and that's how you say that there are different possible microstate to a same macrostate. Okay, think admit. Okay, so this was our option, first option that we marked to be correct. And let us now look at the other options. So the second option was a given macrostate always has exactly one microstate. This is this is obviously false, because just now I told you that for a given macrostate there can be many different number of microstates, not exactly one. Okay, there is no definite macrostate that this is the one microstate for the macrostate, because microscopically the picture is completely different. You can rearrange it in many number of ways and still the macroscopic or bulk properties of the system can remain the same. So the second option is not correct. Okay, so I am just going through the other options as well, because sometimes it is good to know through the other wrong options that what actually the physics is behind the question. Okay, and the third option was entropy is a function of microstates of the system. This is also not correct. Why not correct? Because entropy S is not a function of microstate, but it is a function of all the macrostate of the system. That means it can be a function of temperature or pressure or volume. Just now I told you that these temperature, pressure, volume, these are actually quantities that can identify a system macroscopically. So they can be identified as macro states of the system. And entropy, this is actually a function of those macro states. So entropy is not a function of microstates, it's a function of macro states. Okay. But don't be confused, because the entropy has a formula that A is equal to Kb ln omega, Boltzmann formula, where Kb is the Boltzmann constant and omega is the number of microstates. Now don't be confused, because here omega is the number of microstates, but that is just a count. That does not mean that it is a function of microstates. Okay. Rather, entropy is a link between the microstate and macrostate, because it is involving a formula that has number of microstates in it, but in actual it is a function of the macrostates of the system. It can represent the macroscopic properties of the system. That's why so let me write this, that entropy is a function of macrostates, not microstates. But entropy involves the count of possible microstates, which is omega in its formula. And the last option was different microstates always correspond to different macrostates. This one is also not right, because it is also evident from the first and second option that we described, that a certain macrostate can have different possible microstates. So if that is true, then the last option cannot be true. So it is obvious and evident. So the first option will be the only correct statement for this question. Okay, so question number 2 is done. I hope you can follow me. If at any point you cannot follow me, or if you are having some confusion, you can just stop me and I'll try to explain that to you. Okay, so now the third question is interesting, because here the first example problem, the sum actually comes. Okay, before the two questions were just sort of theoretical and understanding based, but the third question is actual sum. So let us try to solve that now. So first try to understand the question, because in this type of questions it is very important how you see the question, how you understand what is actually being asked in the question. So it is said that from a standard deck of cards, if you have a hand of 8 cards, okay, 5 of which are black, then calculate the entropy of the system. Okay, so you are given a total deck of cards. You know that in a standard deck of cards there are 52 number of cards, right? Out of which 26 cards are black in color and the rest of 26 cards are red in color. So total 26 plus 26, 52 cards are there. Okay, and you are given that you have a hand of 8 cards. That means in your hand there are 8 total cards present, and out of that 8 cards there are 5 black cards. 5 cards are black in color. So that makes it evident, if 5 are black, then 8 minus 5, 3 cards are red. Okay, so let us try to solve this now. Let me go to the page. Yeah. Okay. So this is question number 3. So here we are saying that we have 8 cards in our hand, and 5 out of 8 are black. That means if you just say what are the cards in your hand without knowing anything else, just based on the information that is given, then you have 5 black cards and 3 red cards. So total 8 cards in your hand. But now comes the question that you are asked to calculate the entropy. Yes. So you know the basic formula of entropy all goes around to the standard formula of Boltzmann, that is equal to Kb ln omega. So we have to utilize this expression to actually solve this problem. But how to utilize this? Where this utilization comes? So the trick is to understand this omega. This omega you have to calculate, and then s can be calculated just by taking a logarithm of that. So in some cases this kb, the Boltzmann constant, is taken to be 1. Okay, it is not always mentioned, but apparently if you see the answer, you will see ultimately that kb value is for calculation easy, to make the calculations easier. You do not have to put the value of kb, but kb is chosen to be 1. Its actual value is not 1, but in some cases people choose to take kb to be 1. Okay, similar thing is done also here. So basically you have to calculate the omega, number of microstates, and then you can get s, the entropy. How to get omega? So I just said that there are 52 total cards possible in a standard deck of cards. Okay, now out of which 26, half are two different color, 26 are black cards and the rest 26 are red cards. Now what we have done here is that first we have to choose 5 black cards out of this 26 black cards in total. So there are, in the total standard deck you have 26 black cards, and out of which you have to choose, we need to choose our 5 black cards, because it is said that we have 5 black cards in our hand, but we don't know which 5. It can be of different types, right? It can be of diamonds, it can be of hearts, there can be different type of cards, but the color is black. So how to choose that? So first, it is a permutation combination problem. We have solved these kind of problems in our 11, 12, I think. So the similar trick applied here, that out of 26 cards you have to choose 5 cards. How to do that? How many ways are possible? 26C5. Alright, so it is the number of ways to choose 5 black cards in our hand out of 26 total black cards in the deck. So 26C5. So you have to basically calculate it. It is just 26 factorial by 5 factorial, and then 26 minus 5, that means 21 factorial. Okay, so one part is done here. Then there are these red ones. Okay, so again the same thing. Just let me choose a, yeah. So again the same thing. That means out of 26 red cards you have to choose 3 red cards, because if 5 are black cards, then out of 8 you have left 3. So 3 will be red cards in our hand. So again the similar process will be applied also here for red cards, that out of which you have to, out of 26 red cards you have to choose 3 red cards. So how many ways are possible? That is 26C3, the same way. So it is the number of ways to choose 3 red cards out of 26 total red cards. So it is just 26 factorial by 3 factorial, and then 26 minus 3 is 23 factorial. Now you can just use your calculator and go on to solve what is the value. So ultimately the total value of omega, that is the total possible number of ways to rearrange the 8 cards with 5 black and 3 red in our hand. So it is just the, or in other words, it is just total number of microstates, as the formula says. So microstates, as we can take by this example, that it is nothing but how the system is rearranged in the internal microscopic, not micro, in this case there is nothing microscopic in here, but basically you get the idea, right? So this is just the number of microstates or the number of possible ways to rearrange the total cards in your hand. So in this case it will just be the multiplication of two ways, that means 26C5 into 26C3. We have to multiply because we have both red and black cards, right? So each of the possible ways will be multiplied with each other, and that's how we get omega. And once you get omega, then it is simple to get S, because then S equal to KB ln omega. So you can just take KB to be 1 as they have chosen here. I know because I have calculated from the answer that they have not put the value of KB. So you will also do that. So 1 times ln of omega means it is just a product, right? So it is 26C5 into 26C3. So you can simply calculate it without much help of calculator also. We can try to simplify this, that it is 26 factorial, then 5 factorial, 21 factorial multiplies by 26 factorial, 3 factorial, 23 factorial. So let us try to simplify the thing a bit, that is to ln 26 factorial can be written as 26 into 25 into 24 into 23 factorial. So I am just writing it like that because I want to cancel it out with the 23 factorial over here. Then 5, it can be written as, let's take it as 5 only, or else you can take it 5 into 4 into 3, and then 21 factorial, leave it as it is. Okay, and then again this 26 factorial on the other side, it can also be written as 26 into 25 into 24 into 23 into 22 into 21 factorial. So divided by 3 factorial is 3 into 2 into this 23 factorial. So you can just now simplify things by crossing it off. 23 factorial cancels out, 21 factorial also cancels out. So what are the things that are left? So this is 5, 25 is 5, 5. This is 6, and then we have 2, 12. So basically again you have to do some sort of calculation anyway. So I have done the calculation in my calculator. You can also go ahead and do that. So the answer comes as, let me check, it was 18.95. Okay. I hope the rest of you have also done this in your calculator and got this answer, that is 18.95. And let's see what is the option that is given, 18.95. So this is the last option. So yeah, so this is the option 18.95, option number D. So basically this was the answer to question number 3, also done. I hope this is clear. If this is clear, then we can move on to question number 4. Okay, so let us move on to question number 4 then. So again, read the question very carefully. Alice has 3 black and 3 red cards in hand, picked from a standard deck of 52 cards. Okay, and while Bob has 4 black and 2 red cards, also from a standard deck of cards, then whose hand of cards has a higher entropy? So basically here 2 persons are here, okay, Alice and Bob. Both have given some cards in their hands. Now Alice has 3 black and 3 red cards, whereas Bob has 4 black and 2 red cards. So you can see that both have total 6 cards, okay. this Alice has also 6 cards and Bob has also total 6 cards. Only the difference is that the number of red and black with out of that 6 cards are different. For Alice, the red and black cards are equal in number, 3 and 3. And for Bob, the red and black cards are not equal. 4 are black cards and 2 are red cards. Okay, so we have to calculate the entropy for each of their cases and we have to compare that which one has a higher entropy. So let us now try to solve that. Now because we have just solved question number 3, so I think the type of problem will be now familiar to you, how to solve this case of cards, because this is a very common problem in statmic to actually they give to calculate, they give you these kind of problems to calculate the entropy or the number of ways you can rearrange. So this is a very standard formula that we apply to all of that. So just as we did in question number 3, we'll also try to do the same for question number 4. So first let us take the case of Alice. Okay, now in Alice's case, we'll to identify both of them separately, we'll say that here the total number of microstates possible is omega subscript A, and for Bob the number of microstates possible is omega subscript B, just to identify both of them separately. Okay, now as we know that to calculate the entropy we have to first know the number of microstates for each of them. Like if we have to know the entropy of Alice SA, that is equal to ln omega A. Again we have taken KB equal to 1. Okay, don't bother about that because anyway we don't have to get the actual value, but we have to get the comparison which one is higher entropy. And again for Bob the entropy will be SB, that is equal to ln omega B. So again we have to get omega for each of the cases. Now for Alice you have 3 black and 3 red cards. And how many ways you can choose that, how many ways you can rearrange that? So the same way, basically in the total standard deck of cards you have 52 cards, out of which 26 are black B and 26 are red or R. And out of that you have to pick 3 cards in black and 3 cards in red for Alice. How to do that? So the same, for picking up the black cards you have to do 26C 3 number of ways, and again for picking up the red cards you have also to take 26C 3 number of ways. And because these two are actually independent of each other, because one is black and other is red in color, so that will be multiplied to actually get the total number of ways. Okay, so the total number of ways to get 3 black and 3 red cards for Alice, that is equal to this product. Okay, now this will be our omega A, because this is the number of ways, that means it is the number of microstates as well. So this is our omega A calculated. Now for Bob we'll also do the same thing, we'll calculate omega B. So Bob has 4 black and 2 red cards. Okay, so again out of 26 black cards in the total deck and 26 red cards in the total deck, you have to choose 4 black and 2 red. And how are we doing that? Again 26C4 for black and 26C2 for red, and we have to multiply both of them to get the total. So this is the total number of microstates or the total number of ways for rearranging these 4 black and 2 red cards for Bob. So this is our microstates for Bob, that is number of microstates, that is omega B. So these are calculated. Now we don't have to do much, but we have to compare these two. So to do that we will do, what should we do? That is SA by SB. Because we have to compare, we'll just take a ratio of the entropies. So SA by SB, in Alice's entropy by Bob's entropy, because this is just ln omega A by ln omega B. Okay, and yeah, so again we have to do a calculation, some crossing off, so do this part carefully, because otherwise there will be some problem in the total calculation. So, or let's not take the ln at first, because anyway we know that whichever omega is greater, the s corresponding to that omega will be greater, because s equal to kb ln omega. So if omega is greater, that means s will be automatically greater. So let us not do the ln, because that will only make the problem complicated. So let us just look at which omega is greater than which. So we will do omega s simply by omega b ratio. We will not take the ln. Okay, so omega a, what we got is this part, 26c3 into 26c3. So let us put that 26c3 to 26c3, and for omega b we know that is 26c4 into 26c2. Okay, now we have to do the calculation. You can just as it is, you can just use your calculator and calculate this to get the ratio, or else, because in some cases in competitive exams also you are not given a calculator like that, so in that cases you can also do the calculation in your by your hand also. So that we are gonna do now. So basically 26c3 means we have to do 26 factorial by 3 factorial 23 factorial into again 26 factorial by 3 factorial 23 factorial. Okay, this part is done, and then this omega b part is 26 factorial by 4 factorial, and then 26 minus 4 is 22 factorial, multiplied by 26 factorial by 2 factorial, and 26 minus 2 is 24 factorial. So simplifying things, this is 26 factorial whole squared multiplied by 3 factorial whole squared into 23 factorial whole squared into this part comes up. So basically this is 4 into 3 factorial, we'll break it down like that, and then it is 22 factorial, we'll keep as it is, then divided by 26 factorial, and then this term also goes up, so it is 2 factorial into 24 factorial divided by 26 factorial. So this 26 and 26 factorial crosses off with the 26 factorial whole squared, and by solving it further we get that, okay, so this is, let's say this is our 23 factorial whole square, right? So we can divide it like 23 into 22 factorial for one part, and the second part of 23 factorial we can write it like, we can leave it like 23 factorial. Okay, and similarly we can break these parts down like this this 24 factorial, you can break it down as 24 into 23 factorial. So this 23 factorial and this 23 factorial actually cancels out, and this 22 and 22 also cancels out. So, and out of this 3 factorial whole squared, 3 factorial is cancelled out, and you get just a 3 factorial left here, and which again cancels out with this 2 factorial to give us only 3, because 3 factorial is 3 into 2 factorial, right? So just carefully see what are the terms that are left after all these crossing offs. So this is, there is in numerator you have a 4 into, you have a, I think 24 from this part, and then in the denominator you have 3 from here into 23, I think that is it. So multiply 96 by 69. So this is our omega A by omega b. Now without doing anything else, you can see that 96 by 69 is greater than 1. Okay, because numerator is greater than denominator, so generally omega a will be greater than omega b. Number of microstates to arrange the Alice's cards will be greater than number of ways to arrange Bob's cards. So if that is true, then S A will also be greater than S B. Because why? Because A is equal to just ln omega. So if omega is greater, then S will also be greater. So that is as a proportionality relation like thing. But so basically you get that Alice will have higher entropy than Bob. So this is our answer. So let us choose that option from the question. Okay, so what was the answer? Is that whose hands of cards has a higher entropy? So generally the answer is Alice, that we just calculated. Okay, so question number 4 is also done, and just let me check how many time we have left, how much time, still time is left. Okay, we can, I hope, cover these problems here and do the extra. Okay, so let me go full screen again. Yeah, so question number 5 is one second, just people are not being there. Right. So question number 5 we'll now look at. So let us read the question. It is again a sum. Okay, so now the card problems are done. 2 of the problems, 3 and 4, were based on cards. Now this is a staircase problem. Okay, so it is given that consider a case where there are 3 steps in a staircase, all with equal height h, and there are 3 different people on the staircase with equal weights w. Then how many ways can the potential energy be 8Wh? First of all, you have to understand what you are asked, that there are in a staircase you are given 3 steps. There are 3 steps given in a staircase, 1, 2 and 3. Each staircase has a height of h. That means if the lowermost step has a height h, then in going from first step to the second step, you have added up 2 steps height total, right? So basically you have now the total height as 2h. And again in going into the third step, you are now added up 3 steps total height. So the total height will be 3 times h. And after that you are told that there are 3 different people. Now be very specific about these terms, that there are 3 different people. So in this type of statistic problems, very often people actually miss out these small informations, that whether the particles or the items you are given are distinguishable or indistinguishable. That means if we are talking about atoms, let's say, if they are, then they'll be like if they are electrons or whatever, then they'll be indistinguishable. That means they are all identical particles. We cannot differentiate one from another. They will all look the same. But for people, they are human beings, so basically they are different from each other. They are different in looks, in weight. In this case weight is same, they have specifically mentioned that, but other than that you have different people are different from each other, because they have different names, looks, whatever. So in this case you are given basically particles or items in terms of people which are which are distinguishable. That means they can be differentiated from one another. So that is a very important and interesting information, because that changes the solution of the problem in some ways. We'll look at that how. And then 3 people are given who can stand in those steps in any pattern possible, but you are given that the arrangement has to be in a way that the total potential energy out of the 3 people standing in the steps will be 8Wh. First of all, what is the dimension of energy in this case they are taking is basically weight times h. So basically it is mgh. So it is a potential energy, you know that the weight times the height. Mgh is basically the standard form of potential energy, right? So this is, let's say, capital U. So this is on, in other words, mg is equal to w. So this is w times h is the dimension of potential energy in this case. And you have to arrange the people in those steps in a way that the total configuration's potential energy will be 8Wh. Right, so let us now go to the page and try to solve this. So this is our question number 5. First, enlist what are the informations given to us. That you have 1, 2, 3. You have 3 steps. 1, 2 and 3. So each step has height h. Each step has height h. That means if the first step is at height h, then the second step will be a total height of 2h, because that will be added up, and the third step will be a total height 3h. And you are given 3 different people to stand on those steps. 3 different people. So they can stand on the steps in any manner possible. There is no restriction in that. But the restriction that is given here is that the total number of people is fixed. So let us talk about the restrictions that are here. So first of all, the total number of people, that means, let's say if the number of people in each stair is n1, n2 and n3, because there are 3 steps, right? So if n1 is the number of possible people in step 1 and n2 is the number of people in step 2 and n3 is the number of people in step 3, then the total number of people is given to be fixed as 3. You cannot go beyond or lower than that. That is fixed. This is our constant number 1. And constant number 2 is that your total potential energy is also given to be fixed. That means we have to maintain 8 Wh potential energy. So first of all, if h is the height of the first step, then the potential energy of any people that stands here of weight w will have a potential energy of Wh. So W times h is the potential energy of each pupil if step height is h. That means if you are in the second step, then the step height becomes 2h as you are going higher. So in that case, the potential energy for each people will be 2Wh on step 2 for each people potential energy. And similarly, potential energy for each people will be 3Wh as you go to step 3, because just the height is now 3h. So it is just weight times height. So as going towards higher steps, you are increasing the height. So accordingly, the potential energy is also increasing. So this is one thing. And so now we have to calculate the total potential energy. So it will be N1 times WH. That means for the first step, the potential energy for each person is WH. And if there are N1 number of person possible in the first step, then the energy total will be N1 times WH. Similarly, for the second step, if there are n2 number of people standing there, and in second step you know that each person will have a potential energy of 2Wh. So here n2 will be multiplied by 2Wh. And then for third step, where it is n3 number of people is standing in that step, and there the potential energy will for each person is 3Wh. So it is n3 times 3Wh. So this is our total. And you are given a constant that the total energy should not exceed or should be exactly 8Wh. So this is also fixed. You have to find a configuration where the total energy is 8Wh. So this is our constant number 2. Okay. So now we have to, what was our question? We have to just look at the question once. What is being asked is that how many ways can be potential energy 8Wh. That means you are asked the number of microstates or the number of ways to arrange it so that the potential energy becomes 8 Wh, right? So basically let us now first look at, we can do it both ways. First, for simplicity, I will just try it in an elaborate way so that the idea becomes more clearer to you. So basically, let us think of the fact that how the arrangements can be possible. First of all, this is step number 1, 2 and 3, and there are 3 people for 3 steps. Now the people can be standing in the same step or they can be divided into different steps. So what are the different configurations possible there? So first of all the people, let's say these are the balls that are representing these circles are representing the people here. So all the 3 people can be standing on the first step itself. Okay? That is one possibility. So in this case, what will be the total energy? Total potential energy in this case will be simply the first step has potential energy for each person WH, and there are 3 persons present. That means N1 equal to 3, and all the N2, N3 are 0 because there are no person present in the other steps. So we have the total energy as 3 WH, right? Then now go to a second configuration where again you have 3 steps, 1, 2 and 3. And in this case, you can put all the 3 people, these 3 circles, in the second step. So that N2 equal to 3, but N1 equal to 0 and N3 equal to 0. There are no people on first and third step, only on the second step. In that case, the total potential energy will be, because in the second step, each person has 2 Wh potential energy. So for 3 people, it will be 3 times 2 Wh, that means 6 Wh. So this is the other configuration. So let us try to mark our configurations as, let's say this is configuration number A, this is configuration number B. So now third one will be evident. What I am going to do, you must be knowing by now, that it is 1, 2 and 3, and you have all 3 dots or all 3 circles on the third step. That means all 3 people you have put in the third step, so that N3 equal to 3, but N2 equal to 0, no people in the first or second step. So in this case, the total potential energy will be U equal to, for third step, each people have 3 Wh times potential energy. So for 3 people, it will be 3 times 3 Wh, that means 9 Wh. So this is our configuration number C. So just look carefully that each configuration, there are different number of people in different steps. And the potential energy for each configuration we are also calculating alongside. That is also varying. For the first case it is 3 Wh, and the second case it is 6 Wh, and the third case it is 9 Wh. Now none of them are showing the total potential energy of 8 Wh. This is because right now all the possible configurations are not exhausted. There are many other configurations still left now, which we will look at further. So option number 4 can be, there are 3 steps like this, 1, 2 and 3, and you put 1 people on the first step and 2 on the second step. Okay, and then alongside we can think of like, now we have 1, 2 and 3, then you put 1 person on the second step and 2 on the first step. So the basic routine is now clear to you, I guess. So this is our configuration number D, this is our configuration number E. So in each of the cases, you can know the number of N1, N2, N3, and you can just similarly calculate the total potential energy. Like in this case, N1 equal to 1, N2 equal to 2, and N3 equal to 0. So our total potential energy will be WH plus 2 WH times 2. That means it is 5 WH. Okay. And in this case, the case number E, you have N2 equal to 1, N1 equal to 2, and N3 0. So it is 2 times WH for the first air, and for the second step you have 2 WH times 1 because there are 1 person present. So it is just 4 WH total. Okay. Then again you have configuration number F possible, where you can now arrange it like you have 2 persons on the third step and 1 person on the second step. And in this case, in 1 0, into 1, in 3 2. So in this case, what will be the total potential energy? It will be 0 plus 2 Wh plus 2 times 3 Wh. It is 7 Wh. Alright. And further moving on, configuration number G will be 1 2 2 3, and then you have what was the case? Okay, you can just do the opposite to that. Am I doing something? Oh, so sorry, this was not
Excuse
7,
me.
this was 8.
Yes, yes.
Yeah, thank you, that was a mistake. So this is 8 Wh, and then similarly moving on, we can now put 1 person on the third step and 2 person on the second step. Then the total potential energy will be 2 Wh times 2 plus 3 Wh, and this is our 7 Wh. So we have still 3 configurations left. What are those? So this is H, configuration number H, 3. So this is 1 person on top and 2 person on bottom, and U will be 3 Wh plus 2 Wh, that is total 5 Wh. 2 more will be configuration number I is 1 2 3. Here you put I think, what are we left with? Here 2 and let me check. I think here 1. This is not done before. Just check. Yeah, so all possible configurations of 2 and 1 are done except this. So here the total potential energy will be 3 Wh times 2, that means 6 here and 1 here. So it is again 7 Wh. Just look at the fact that it is a 7 Wh total energy and number G is also 7 Wh, but the configurations are different. That was what gives you the idea of same macro state but different micro states to some extent, right? Because both of these cases, number G and number I, you can see that the total potential energy is same, 7 Wh, and the total number of people for the steps are also same, that is 3. But how you are organizing your people in those steps are different. Like here in the second step you have 2 people and the third step you have 1 person, but in configuration number I you have just 2 person in the third step and 1 person in the first step. So they are both different configurations microscopically. That means as if they are different micro states, but macroscopically they are same because their energy and the total number of people are same. Those are the macroscopic properties. So this is an example that can be clear to you that how I am saying that they are from different micro states but they belong to the same macro state. Okay, and the final one, let us draw that. It is very easy because now each person will be occupying each step. So this is our configuration number J, and here the total potential energy will be Wh plus 2 Wh plus 3 Wh. So it is 6 Wh. So these are the all possible type of configurations that we can make, arrangements we can make out of these 3 people in 3 steps, and we have also calculated the energy corresponding to that. Now just look at very carefully. I have done in an elaborate sort of pattern so that you can look at all the possible energies that are there, but we could also directly look for the 8 Wh energy, so then it will be less time taking, but for the understanding purpose I think for the first time it is better that we cover all the areas. Okay, so here we can just look at that 8 Wh only comes once. This is our 8 Wh energy. This only occurs once. When it occurs, it is when 3 person are on the 2 person are on the third step and 1 person is in the second step. Then only the energy configuration is such that you have total energy of 8 Wh, and this is our configuration number F. Okay, so this was one thing, that you have only one case when this 8 Wh occurs. But then again look at the question. There is a trick that how many ways can be potential energy 8 Wh, but also you have to look at, now this factor comes, that why I was emphasizing on the fact that there are three different people, they are not identical to each other. So let's say if the people are some A, B and C, three different people, they are all distinguished from each other as different quantities, entities. So that's how you cannot say that there is only one way possible for 8Wh, because in this 8Wh configuration also, these circles are not identical circles. Here they are looking identical because I have identified them as circles, but if you give them different names, because they are three different people, so let us give them names at A, B and C. So then how they will be arranged, like when A and B will be sitting together, or when B and C will be sitting together, or when A and C will be sitting together, out of those configurations there will be three number of ways possible. Just to be clear, let me draw it. What are the three ways for getting 8Wh? So the answer is three ways are possible to get 8Wh energy. I am just drawing that. It is the configuration of 8Wh total energy. And because three different people are there, so they can be distinguished from each other. So we can identify them by A, B and C. Now the basic configuration was, if you look at that you have 2 on top and 1 on middle and 0 on the first step. But which two are together and which one is different, that matters when A, B, C are different. So we'll now place, let me use a different color. So we can place A first alone on step number 2 and B and C together on step number 3. Then again we can place B alone on step number 2 and A and C on step number 3. And the third case will be C alone on step number 2 and A and B on step number 3. So you can see there are three ways possible, right? Three ways to do this. And why there are three ways? Because they are different. They are A, B and C. They are not all identical. If the question was different, that instead of three different people, if they tell you that there are three identical marbles given, so all the marbles are same to each other ideally, so then the answer will be 1. Then the answer for 8Wh energy would be 1, because then this kind of a configuration will not be possible like we can do with A, B and C, because then all the marbles are identical. So it does not matter in which way, which two marbles you put together and which one marble you keep aside. So that makes the answer different, that for three identical people or three identical marbles, the number of ways to get 8Wh would have been 1. But because there are three different people, so now there are three ways to do this. To get the 8Wh, the answer is there are three ways to arrange the people like that. And I have just told you how. Okay, so this is a very important point of these kind of problems, that you have to look at the question very carefully, that they have mentioned not identical but three different people. Okay, so let us mark the answer now. It is 3. Alright, so now question number 6. It is asked that for the same system as the above question, that is question number 5, what value of potential energy will have the maximum possible ways of occurrence? Now because the same systems problem is given in 6, that's how now the elaborate description or elaborate calculation will come handy, because now we have the total set of possible potential energies in our hand by the calculation and pictures we have drawn. So we now know what are the possible potential energy for all type of configurations that are present here, and it is asked that for what potential energy the maximum possible ways of occurrence will be happening. Okay, so now just go to the pictures and it will be clear to you that which is the maximum. So no, first look at the options also, because not all the options are given. So it is 3, 9, 6 and 4. These 4 are given. So let us now look at which of the energy has more number of ways. So 3 is here one time present, okay. 6 one time and another 6 should also be there. Yeah, this one. 6 is there 2 times. 4 is one time and again 5 is 2 times. 7 is also 2 times then 8 is single time. Yeah, I think 8 is single time and 9 is single time. So basically out of those 4 options, I think 6 was an option that was given in there. So 6WH is the only option out of the 4 options that actually occurs twice in those potential energy pictures. Two type of configurations. One is this one, configuration number B. Okay. And another is, where is 6? Yeah, this is configuration number J. Now, although they have not told you that how many ways are there, but I am still calculating that for you, that even if 6 occurs 2 times, 6WH occurs 2 times, but for each of the times there can be again different permutation combination, right? Because again 3 different people. Now in this case of configuration number B, when all 3 people are sitting on step 2, there you have nothing else to do, because A, B, C, they will all sit together on the same step, and it does not matter whether you put A first and B first or C first. That does not matter, because all are on the same step. That means all are on the same energy level. So that combination does not really make sense in this picture. So here there is only one way to get 6WH in this configuration number B, because all 3 are sitting on the same place. But in the last option, that is the configuration number J, here, because each of the person is occupying each of the step, here the number of ways becomes more than one. It is 3 ways basically, because let's say you have A, B and C. So in one case you can have A here sitting, B sitting here and C sitting here. And then in the second option you can have A going on top, B going down, let's like that. Basically they will all exchange their places, and in each of the 3 ways each of the person will be coming for once in each of the steps. So there are simply 3 ways possible to get 6WH out of this configuration number J. So if you calculate totally, so 6WH occurs 2 times, configuration number B and configuration number J. In configuration number B, there is only one way possible, because all 3 are sitting on the same step. And in configuration number J, because each person is occupying each step, so there are 3 possible ways. 3 ways are there. So total there are 1 plus 3 equal to 4 ways. So this is not 9, so this is 4. Sorry, just yeah. So there are 4 ways. Okay. So clearly from that options, 6WH is the energy option that can have the maximum number of occurrence, and I have also calculated for you what is the number of occurrence, which is 4 in this case. And if there are options given for 5WH or 7WH, then the calculation would be different, because 5, 7, these are also coming twice, and then in each of them there are different number of ways to permutation combination thing to do again. But out of the 4 options that are given in the question, 6WH will be our answer, because that occurs 4 number of times, 2 times and 4 ways. That is maximum from the other options. So this is our this is our 6WH, because it occurs 4 ways, 4 possible ways of occurrence, whereas this 4, 9 and 3, these all occurs 1 times for each of the cases. And then let us not look at the combination permutation case, but for 6WH it is a maximum occurrence. So 2 times occurrence. Okay. So question number 6 is done also, and then question number 7 and 8 are left. So 7 is a numerical problem and 8 is again a understanding problem. Okay, so let us look at question number 7. So it is asked that consider a staircase with 3 steps and 3 identical marbles arranged on them. Again a staircase problem, but just like I was telling you that instead of people, they are now telling you that they are identical marbles. So look at the difference in problem. This is a similar problem, because again 3 steps and 3 entities, but instead of different people, they are now saying that you are given 3 identical marbles. They are all identical particles similar to each other. You cannot distinguish one marble from other. You cannot identify them by A, B and C. They are all same and similar to each other. Okay. And other thing are saying same, that is the steps are of each of height h and the marbles are of weight w. That means potential energy contribution will be wh, 2wh and 3wh for each of the steps and each of the marbles. And then they are telling you how many ways can the potential energy be, 6wh. Okay, so now again the question becomes very easy for us because we have already in detail drawn the whole picture and number of possible configurations for the exact same problem that we tried to do for question number 5 and 6. Because number of steps are same, 3, number of entities are also 3, so the pictures and the configurations will be same. Only the final permutation combination that we had to do for different people to by naming them as A, B and C, that part will be eliminated, that part will not be needed, but until that part everything will be same. So the question is simply asked that how many ways can the potential energy be 6wh. So I think you know the answer by now, that okay, 6wh. So let us now look at what was the configurations given there and then we can find out how many ways. Okay, so 1, 2 and 3. 6wh, 3 steps, 3 same marbles, so this is one.
Only one.
1 second. What is the answer? Hello? Someone gave the answer now. You said only one. Just WH, 3W. So if there are 3 marbles in 3 steps, then clearly WH, 2WH and 3WH, 3 plus 2 plus 1, there is 6WH coming. But what if this configuration is also there? That means 3 marbles on the same staircase. So 2WH is each of the marbles weight, right? So 2WH for each of the marbles on the second step. And if there are 3 marbles on the same second step, then it is 2WH times 3. That means again 6WH. Right? So basically you are having 2 possible ways now instead of 1 from this configuration, because the problem is same as question number 5 and 6. This is the same problem. Only the difference is that instead of 3 different people, you are not now considering 3 identical marbles. So that means you don't have the necessity to do the further calculations to get the number of ways for A, B and C, because that would be different. Okay, but until that the picture remains the same, right? Because now these marbles are these circles, all are same circle. So they can either all occupy the step number 2, so that they have a potential energy of 2WH times 3, that means total 6WH. Or the other possibility to get 6WH is this configuration number J, where each of the marble can occupy each of the step. Then also the total configuration energy becomes 6WH. Right, so there are 2 ways possible, I think, not 1. So is it clear? Why 2? If you have a confusion, just feel free to ask, because I'll be happy to explain. Because I think the picture is pretty clear that there are 2 configurations possible, 2 ways possible. Either all 3 on the same level, that is level number 2, so that 2WH times 3 becomes 6, or each one on each step, so that the total energy becomes 2 plus 3 plus 1 is 6WH again. So there are 2 ways possible, right? So this is the thing. Alright. And now the last question of this assignment is question number 8, which is asked here that for a system of marbles of an endless staircase, there can be cases of negative temperature, true or false. So this is a question that you can readily answer if you have just followed the lecture video of week 1, because there itself this example is given that for endless staircases or endless number of possible states given, then when there is no restriction like that, then the temperature cannot be negative. So negative temperature will be false. Let me go to a bit detail why. So this is question number 8. So first of all, what is defined as temperature here? Here temperature is the inverse of the slope of the, so this will be in power. Yeah. So this is the inverse of the slope of the entropy versus energy plot. So if there is an entropy S versus x-axis is energy plot, then if let's say the plot looks something like this, or maybe it can be a Gaussian also, whatever way you can choose. Okay, so if this is the plot, then this is our maximum point where the entropy is maximum. Obviously this will be an equilibrium state, because in the first problem we answered that in equilibrium state the entropy will be maximum, right? So the equilibrium state will be here, the peak. And then the slope, if we calculate the slope, it is just del S by del E, that is the slope of this plot, and temperature is simply the inverse of that slope. And why temperature is like that, I will also explain that to you, because you see from the first law of thermodynamics, you know the energy conservation says that dq equal to du plus dw. Energy equal to internal energy plus work done. Heat energy equal to internal energy plus work done. So also we know that dq equal to TdS, right? Now this dW work done will be 0 for the cases when there are no volume expansion, or let's say when there is no external work done on the system, that is dV equal to 0 or anything like that. So then dQ equal to simply du, where U is the internal energy and du is the change in the internal energy of the system. So then just dQ equal to du, and dQ equal to also TdS, that is known from the second law of thermodynamics, where the entropy idea was introduced, that ds equal to dq by t, so dq equal to t times ds. So basically if dq equal to dw, then you have du equal to tds also, and t equal to del u by del s. So here the E we are using is nothing but the energy, right? It can be the internal energy of the system itself. So it is basically nothing but del E by del S. E and U are basically the same thing, energy, internal energy of the system. And temperature is del E by del S. That means it is inverse of del S by del E. So that's how we get that if we have an entropy versus energy plot, if we calculate the slope, that inverse of that slope will be our temperature. Now this is the idea. Now in this kind of a plot, when there is a maximum point of entropy where the equilibrium point occurs, and at all other points entropy is lower than the maximum value, right? So in the first case, that is below the equilibrium point, when the entropy was increasing, that means it has an increasing slope, positive slope. So here the slope was greater than 0. That means that temperature, which is inverse of the slope, will also be greater than 0. But beyond the equilibrium point, as we are moving beyond the equilibrium point, going away from the peak value, then gradually the slope is decreasing. That means here the inverse of slope or temperature will be less than 0. So in those problem cases, example cases, when, let me write this, when in this type of a plot, when entropy is not monotonically increasing with energy, their temperature can be both positive and negative in different parts of the graph, as we just saw, right? And when this happens, when this kind of a system happens, that entropy is not monotonically increasing with energy, is when you have a restriction on the number of available steps, for example, so that the total energy that you are actually giving, total energy is actually restricted in the x-axis. Say for example, if you have finite number of steps present, that is let's say you have two marbles given and you are told to arrange them in 3 steps. That means the number of steps is limited. You know that you have 3 steps, you cannot go beyond that, you cannot get more steps. So whatever configuration you choose, you will always end up with a maximum possible energy, right? Beyond that, the energy will not be increasing because the number of steps are restricted itself. But if let's say your number of steps were infinite, if step number was infinite, then what would happen is that in this manner 1 2 3 infinite number of steps possible, right? And each of the steps, you know, for let's say in case of marbles example, you know that each of the step you have a potential energy going as WH, 2WH, then 3WH, dot dot dot, then it will be infinity also, because if the number of steps is itself going to infinity, then the potential energy corresponding to that step will also be infinitely increasing. There will be no bound in that, no restriction in that. So in that kind of an example, you will have a case when the entropy will not be monotonically entropy when not monotonically monotonically increasing with energy, like this case. This kind of a case is only happening because you have a restriction in the total energy that is given. So entropy was initially increasing, then reaching a maxima at the equilibrium state, and then again lowering down to finally again decreasing or coming to zero at a higher energy state, because there is a bound in what is the maximum possible energy that you can achieve in such a system, given that your number of steps or the energy you are accessible to is limited. So in that case, temperature can be both positive or negative. But if number of steps is itself infinity, so that the total accessible energy of the system has no upper bound, then the entropy can be infinitely increasing with energy. That means it will not show a peak and then fall down, but the entropy will also go on increasing. And this cannot be done manually by hand calculation cannot be done, but it can be done by some coding in some software like this Python or Mathematica, these things, that if you take this step number to infinity, then gradually you cannot find the equilibrium yet, because still your entropy is increasing and increasing in number of, as you are increasing still the number of steps and going towards higher energy. And because there is no fall down of this monotonic increasing energy, and here entropy is monotonically increasing with energy, because energy has no upper bound. In that case, the temperature will always be positive. Temperature, that is the inverse of slope, del S del E inverse versus E, will always be positive. There is no point that it is negative, because you can calculate the slope here, everywhere it is just positive, right? Whereas in this case, when there is a bound in the maximum attainable energy and there is a bound in the total number of steps, then we saw there is a peak and then falling down. That means if you plot the slope inverse here, or in other words, if you plot the temperature versus energy for this case, it will be looking like initially the slope was positive here, then it was going to a maxima, that is where the slope becoming 0, and then again it is falling down. So it can be something like this. This is also given in the lecture, that here the slope is equal to 0. Sorry, not slope is not 0, slope is infinity. So the inverse of slope, that means the temperature becoming 0. So this is a confusion. Basically we are calculating the inverse of slope, right? So at the maximum point the slope is infinity, so that's why you get the inverse of slope, temperature, as 0. And below this the slope is positive, so temperature is also positive. And above this point the temperature is negative, because here the slope is becoming negative. Okay, so this is our idea, that whenever there is a bound to the total number of steps given to you, or the total maximum attainable energy, there is a restriction that you cannot go beyond this maximum energy in the system, then the entropy will go to a maximum and then again falls down. It will not be a monotonic behavior of the entropy, and that's why you get positive and negative regimes of temperature. Whereas for the case when there are infinite number of steps, so there are no finite limitation that this many number of steps are given to you, so that there are no finite limitations to the total potential energy that is maximal attainable to you. In that case, the entropy will only monotonically increase with the energy, and as a result the slope or the temperature will only be positive, no negative value. So this is the false answer. So with this we have covered all the 8 questions that are given in the assignment. So before I move on to the other set of problems that I have, some problems I have prepared, but before that I would like to know if you have some confusion regarding the problems we just discussed in those 8 problems, so that we can go back and look at that, or otherwise I can just move on to the other problems. So if you have anything, you can just let me know. I'll wait for 2 minutes.
Hello, madam. Is there any physical meaning in saying that temperature, negative temperature?
I don't think there is a physical meaning actually to that, because basically this is the definition we are talking about, that it is in temperature is here the inverse of the slope of the entropy versus energy graph, right? So in one term temperature cannot be in that sense, it is not meant like that, but it is just about the behavior of the entropy with energy, how it is behaving. I think that is the case what is going on here, that you just have to look at how the entropy, either it is monotonically increasing with energy, or it has a peak like feature and then again it falls down. So depending on that, it is basically, I think, happening. But if there is any physical meaning, I think if that is needed, then I think that in the lectures it will be discussed, but right now this is all that I can tell you.
Okay, thank you, ma'am.
Okay. So if there are no other confusions regarding the problems we solved, so we can just look at few of, because there are still time left in the class, so we can just look at some other similar problems of this calculative sort of things, because there are different types. All the types are not maybe covered in these 8 problems, but we can just look at how the problems are solved generally. So I have collected some problems from other books or internet stuff. I can just solve that with you so that you can get the idea. Okay, so let me go to this page. Okay, so this is our extra problems. Okay, right. So let us see how many we can cover. Now the first one, I'll just tell you the problem sum and then I'll do the solution as well. So just listen very carefully, because there is no printed form of the problem. I'll just tell it to you, and then I'll also note down the basic details. Okay, so in the problem you are given a rod. You are given a rod like this, and the length of the rod is given, that is capital L, and the thermal conductivity of the material of the rod is K. Also the cross section area of the rod is given as capital A, and the rod has two ends, end number 1 and 2, both the ends have different temperature, T1 and T2. Okay, and you are asked that if the rod is in steady state with this condition, then what will be the entropy increase of the universe from the rod. Okay, so this is basically a very basic thermodynamic problem, but we will start with that because it is a basic problem, but it is a standard problem. It is very often comes even in competitive exams also. So basically we just note down our problem first so that there is a basic reference. So a rod is there, both ends have different temperature. So we can assign one end as the hot end, and the other end as the cooler end or cooled end. One has temperature T1 and the other has temperature T2. So we can assume that because one of the temperature will be greater than the other, so let us assume that T1 is greater than T2. Okay, that means our hotter end is T1, this end, and our cooler end is this second point, that is at T2. So T1 is greater than T2. Length of the rod is L, cross section area is A, thermal conductivity of the rod's material is capital K. So what will happen if you leave the rod in this case, in this condition? So the basic idea is that what will happen is basically because both of the rods, see, they are at different temperatures. So nature's tendency will be that they will try to exchange like heat in between the two ends so that the total rod's temperature reaches a equilibrium. Because whenever you have a hotter object and a cooler object, the basic tendency is to spontaneously transfer heat from a hotter body to cooler body so that they can come into a thermal equilibrium at some other temperature. Okay, so the same thing will happen in these rod scales also, because rod has both ends has two different temperatures. So basic tendency is to transfer heat, and mind you that this heat transfer will be a very spontaneous process. That means you don't have to do any external work to make this heat transfer happen, because this is a spontaneous process. As you also know from the second law of thermodynamics in other terms, this is also discussed in the lecture, that there will be only a spontaneous transfer of heat from a hotter body to a cooler body, not the other way around. Because the other way around, that is to transfer heat from a cold body to a hot body, that will not be a spontaneous process. You have to externally apply some work or something to do that. But if you leave the system as it is, so it will spontaneously transfer heat from 1 to 2 end. So 1 and 2 I have marked as, let's say, these are the two ends. Number 1 is this end, number 2 is this end. 1 is our hot end and 2 is our cold end. Okay, so basically first we have to know what is the heat that is transferred, because entropy is ultimately ds. We know that it is dq by t, right? Because tds equal to dq. This we just derived. So to get entropy change, you have to get what is the heat that is transferred or absorbed, whatever, divided by the temperature. So in this case, the heat, if that is q, that is being transferred from 1 to 2, that has a formula, standard formula, that is, it is k times a into T1 minus T2 by L. So this is the formula that you know from thermodynamics. This is the standard form of heat. If the thermal conductivity of the system is known as K, area is given, length is given, then the temperature difference is T1 minus T2, because T1 is greater than T2 here. So this is our transferred heat from one end to the other. So if that is the case, then the side number 1 or end number 1, hot end, will release, because this is the hot end, so this will release the heat release the heat of amount Q. So what will be the entropy change for this end? So let's say it is delta S1. This is the change in entropy for end number 1. This is simply the heat divided by temperature. So in this case, dQ1, the change in heat is basically minus Q. Why minus? Because it is releasing the heat. Because releases heat. And its temperature is, we know, T1. So it is just minus Q by T1. But for the other end, that is end number 2, cold end, will absorb the same heat that is being released by end number 1, because that is the thing that is happening, right? That you are transferring heat from one end to other. So if one end is releasing the heat, then the same heat is being absorbed by the opposite end. So in this case, because the heat is being absorbed, so dQ2 is plus Q, because it is absorbed. And in this case, the change in entropy, let's name it as delta S2, then it will be dQ2 by T2, which is plus Q by T2, right? So we have to calculate the total change in entropy of the system in a steady state. So total change in entropy of the rod. So you have to take into account both the ends. That is, if the total change is delta S, then it is delta S1 plus delta S2. So it is simply minus Q by T1 plus Q by T2. So this is Q times 1 by T2 minus 1 by T1. Simplifying it further, you can get Q times T1 minus T2 by T1 into T2. So this is our delta S in total of the total rod. And how are we getting this? Because this is a steady state entropy change. Because at steady state, the system tries to reach thermal equilibrium, and that's why it absorbs heat on the colder end and releases the same heat from the hotter end, so that they can get to a equilibrium temperature. And in that process, in that heat absorb and release process, you get the total change in entropy from the two ends for the entire rod. This is this answer. Okay, so this is our answer. I think this was a very simple question. You can also simplify it even further, because you know that expression of Q, so you have to put that into this expression. This is just K times A times, this is also T1 minus T2, and here is also T1 minus T2, so both will be T1 minus T2 whole squared, divided by L that was present in Q, into T1 T2. So this is our final expression. This is one problem that we have solved. This is a very basic problem from thermodynamics, but you just have to calculate the entropy, because anyway we are calculating entropy in most of the cases, right? So this is that. Then we can look at another problem. This is also, now these problems are, let's say, these are based on calculations of entropy for different example systems. Like previously in the old assignment that was given, that is solved earlier, in that case you are also asked to calculate the entropy in some cases. There the problem of the system was that you are given a system of staircases and people, or staircases and marbles, like that. And these are relatively simpler from that, because here firstly you are given a rod in which you are told to calculate the entropy. Similarly, in the second problem, you can say that you can choose a system of water, and how in that case if you mix two different temperature of water, and how that can change the entropy of the system or the universe, that you are asked to calculate, then what will happen. Okay, so that is our question number 2. If we want to address the problem, is that we have a water in a particular container. This water mass is equal to m. So this is, let's say, container number A, where water is kept of mass A and the temperature of this water is T1 Kelvin. Okay, and another container is there, container number B, where also water is kept of the same mass. Okay, same mass, same volume, whatever, that is same mass m, but the temperature of this water is different. It is T2 Kelvin. And you are asked that both water are mixed adiabatically. Now these conditions are very crucial because sometimes by missing these the answer can be completely different. Okay, so both water are mixed adiabatically and isobarically. So in that case, what will be the change in entropy of the universe? That is what is delta S. And I think adiabatic and isobaric means what they mean. It is known to you that adiabatic is when there is no exchange of heat with the surrounding, that is dq equal to 0. That is externally out of this whole water body, the water cannot take or give heat to the other parts of the universe. That means the two water bodies can interact with each other, but other than that there can be no exchange of heat with anything else possible. Anything from the environment, it is not allowed. That is dq equal to 0. And isobarically means you have a constant pressure maintained. So the whole process of mixing the water is done at a constant pressure. So now again you have to calculate the change in entropy, right? So basically again you have to, for that you have to know what is the heat that is being transferred, because otherwise you have to get ds equal to dq by t. Now don't get confused because we have already told dq equal to 0, but that is from external source, that is not from the system itself. That I was telling that nothing from the environment can affect the water bodies, that whatever heat that is being exchanged, that can only happen between the water body 1 and water body 2, but nothing else, or no external source can be there. So the two water bodies, because they have a difference in temperature, one is T1 and the other is T2. Again let us assume that T1 is greater than T2. That means container A has a hotter water compared to container number B. So again when you mix them, when we mix them, they will try to achieve a thermal equilibrium. Okay, that means they will absorb and release heat within themselves. So the condition is that heat lost equal to heat gain. This is the basic condition of thermal equilibrium. You know that whatever heat that is being released or lost by hotter water at T1, the same amount of heat should be absorbed or gained by the cooler water, that is at T2. Water at T2. Then only they will exchange that heat and try to achieve a thermal equilibrium. Okay. So in case of water, because this is a constant pressure process, so we can see the heat capacity, we can define it C subscript P. This is the constant pressure specific heat or heat capacity, that is Cp, and the mass is given m. So we know that the dimension of heat is Q equal to m Cp delta T. That means mass of the system, heat capacity or specific heat, and the change in temperature. This is the total dimension of heat. So in this case, the heat lost by the water body at temperature T1. So let us first say that after equilibrium reached, that is when water A and B are already mixed together and they have exchanged their heat, final temperature of that entire water, final temperature equal to, assume that it is T Kelvin, because you have now mixed temperature T1 water and temperature T2 water, so they will exchange heat within themselves and they will try to reach a equilibrium state where the final temperature of the entire mixed water body is at T. So in this case, the heat loss by water body at T1 is m times Cp into T1 minus T. Okay, because here T1 is greater than T anyway. T1 was a hotter body and T2 was less than less than T1. So basically here T will be greater than T2. So like T2, T, T1. This is a sequence. When they exchange heat and come to an equilibrium, the final temperature is lower than the initial hotter temperature T1 and it is greater than the initial cooler object's temperature T2. So it is heat gain is mCp T1 minus T. It is heat loss, not heat gain, because it is lost from the hot water, and the heat gain is an mCp T minus T2. Here m is same for the both waters have same mass. This is heat gain by the cooler water at temperature T2 and it has reached the final temperature which is greater than T2. So that's why T minus T2. And then again if you take terms on the same side, then it is just 2T equal to T1 plus T2 and T equal to T1 plus T2 by 2. So this is our final equilibrium temperature of the combined water body. Once that is done, so now you just have to do the entropy calculation. So again, total entropy change is delta S, which is the sum of delta S1 plus delta S2. That means from water body A and water body B, you have to separately take the entropy change and sum both of them together to get the total entropy change. So this is equal to, now delta S1, what will be the expression? So this is basically dq1 by T. Now let's say this T is not constant here, okay? And also don't confuse this T as this final T. Let's say for avoiding confusion, we denote it by T naught instead of T. So T naught is our final temperature after equilibrium is reached. And T is basic the same simple temperature variable T. Okay, so don't get confused. So this is, there will be integration sign involved because now the temperature is not fixed so that we can take it out, but the temperature is changing with the process from T1 to T0. For the first object, first container of water A, it has initial hotter temperature at T1 and then after equilibrium it has reached T0 temperature. And for the water at container number B, there it is integration of dq by T. T is the temperature variable, and where the temperature is changing from T2 to T0, from a colder temperature to a higher equilibrium temperature of T0. Now this dq1 and dq2 values, we know that this is the heat lost from the first system dq1, that is mCp, and instead of taking the difference you take it as dt, the change in temperature, because you have to integrate, right? So you don't put the temperature difference directly, but you have to integrate and then put it. So this is just as a variable mCp dt by T and then integrated from initial to final temperature. Then same again for the heat loss gain case, that is the second water body, you do mCp dt by T from initial temperature T2 to final temperature T0. So mCp comes as common and then integration dt by T is just ln T. So it is ln T from T1 to T0 plus ln T from T2 to T0. So simplifying it further, it is mCp ln of T0 by T1 plus ln of T0 by T2. So we can simplify it even further. because it is ln something plus ln something, so we can take the whole thing under product of ln. So it is T0 into T1, T0 by T1 into T0 by T2, right? That is the purpose of ln. Ln A plus ln B equal to ln of A times B. So this is just MCP ln T0 squared by T1, T2. Okay. Now we already calculated the value of T0, which is just T1 plus T2 by 2, right? So just by using that, you just put the expression of T0 here and you will be done. That delta is equal to MCP ln of T1 plus T2 whole squared divided by 4, because here 2 becomes 4, T1, T2 is as it is left. And to simplify it even further, you can take the square to the in front of ln, so that you have a 2mCp ln of square has come out by the 2 factor, so it becomes 2 root over of T1, T2. So this is, I think, our final answer, that this is our total change in entropy for this case, for this example, when you have two water bodies at different temperatures, T1 and T2, one is hot, one is cold, and you have mixed them, keeping the pressure fixed and no heat exchange from the outside environment. Then what will be the total change in entropy that is involved in that process? So this is the answer to that. Okay. So this part is also done. So we have just now covered things that are basically, yeah, so we don't have much time left. Maybe we can just take one example problem, one more problem, and we'll finish today's class after that. So we can take an example where it's say the arrangements problem will be nice. How many ways you can arrange, so that you can have the idea how to calculate the microstates like that. So let us take one example like that. This is a nice one, that you have, this is a small, this is a short one also, number 3. The idea is that you have a monoatomic crystalline solid given to you, okay, and that solid has total n number of, that solid, that not this monoatomic, this solid has a number of atoms. It consists of a number of atoms. Consists of a number of atoms, and out of that n atoms, small n number of atoms are positioned in the interstitial sites. Okay, interstitial sites. These are the two quantities. And it is also given that the number of available interstitial sites in the solid equal to n prime. So these are the major infos that is given to you, and you are asked that what is the number of possible microstate here. But in other words, how many ways you can arrange the system given these conditions. Like you have the total number of atoms fixed as capital N. Out of that capital N atoms, smaller number of atoms are interstitially positioned. So there are specific positions in the crystal where they are the lattice, in between two lattice sites there is a position which is called the interstitial site. So smaller number of atoms are like that they are only positioned interstitially, and in the total solid, in the entire solid, there are capital N prime number of such interstitial positions available for the atoms to sit in. So basically you have to arrange now, and you have to look at how many number of ways you can arrange so that all these conditions remains applied, but you get as many number of ways as possible. That is your total number of possible microsets, right? So this is very simple. Again, the combinational problem. First of all, you have to understand what to do. Firstly, you first number of ways to choose small n atoms out of capital N total atoms in the solid. This will be capital N, C, small n. This is same as the problem of cards. Remember that you had 26 black cards and you had to choose 5 or 4 black cards out of that. So you had simply done 26C5, right? So similar thing is done here too, that you have total n number of atoms, capital N, and out of that you have to choose small n number of atoms. So you just do capital N, C, small n. This is capital N factorial by small n factorial, then capital N minus small n factorial. Then what is has to be done further is that, secondly, number of ways to place the small n atoms in capital N prime number of interstitial positions. That means it is similar to that, let's say you have n prime number of staircases and you have to put small n number of atoms in that. So how many ways you can arrange? Again the same thing is that capital N prime, C, small n. Just look at that example, that out of the system that you have to choose, that is placed on top of this combinational thing, and then the small n is in the lower subscript. So this is basically the simple combination aspect, nothing to be done more than that. So this is the number of ways you can place those atoms in the available sites. So this is simply n prime factorial by small n factorial, n prime minus small n factorial. So now what is the total number of ways? So these are two independent events. So the total number of ways will be just a multiplication of both of them. Is just NCN times n prime Cn. So the answer will be n factorial by n minus n factorial to n factorial into n prime factorial by n prime minus n factorial into n factorial. So this is your final answer. So this is just a simple, very simple problem to get you to let you know the idea how these combinational problems are done. I have prepared some other problems, some more difficult, not these easy or evident problems, but some more difficult problems to discuss. But today's class is, I think, time is over, so we can get that done in the next class maybe. But we can just finish the class here, tutorial here. So if you have any further queries, you can tell me, or we can end the session here. Okay, so I think nobody has any doubts anymore. So we'll again meet on next Saturday, 7 to 9. Today I had a little delay because there's some technical issues in the class, starting the class. But from the next Saturday onwards, we'll continue on the further lectures ahead. And this assignment is already solved. The further week's assignment based on the week 2's lecture are also released. I think that will be covered in the next session. But I will try to cover some extra problems as well alongside those assignments in our further sessions. Okay, so bye then.